Okay, we're going to apply what we've learned about related rates and actually solve some problems. So you're probably going to need like a calculator or something. I'm going to go without a calculator, but you'll need one. Okay, so let's talk about the problem solving process first. All right, first and foremost, you need to draw a picture. If you're dealing with some kind of geometric figure or geometric example, directions, you head north, you head south, east, west, something like that, draw a picture. All right, and of course name the variables, and most importantly name the constants. All right, if you are considering time, always use the letter T. All right, assume that all of the variables are differentiable functions of time. They all are associated with some rate of change in terms of time. Okay. Number two, write down all of the numerical information. So they'll give you some information, and they'll supply you with information that you need to know, like suppose so many objects are produced, or you've traveled so many miles so that's information you need to write down. Of course, also write down what is it that you are being asked to find, and then often they're asking you to find the rate of change of something. So write that down, give it a name. Then, of course, write an equation that relates the variables. Now, sometimes in these problems, they're very generous and they give you a formula, but that's not always the case, and don't always assume that's going to happen. Okay? Sometimes they may give you some information, and you have to know that I've got to apply, for example, the Pythagorean theorem. Or if I'm talking about the rate at which a cube is expanding, for example, well, that's probably going to require you to know the formula for volume of a cube. So they may not give you the formula directly, so be sure that you write down some formula that you can use to represent an equation that relates all of the variables that they're talking about in the problem. And then finally, of course, differentiate with respect to time. Take the derivative, okay, of all of the variables present. And last but certainly not least, evaluate. What does this mean? In short, this means to plug in. Okay, so I always draw my little electrical plug like that. Okay, so plug in. All right, so let's go ahead and take a look at a few problems in regards to related rates. And hopefully this video is not terribly long by the end of this, but we're going to look at 3 good examples. So let's take a look. Here's the first one. It says a company knows that the unit cost C and the unit revenue R from the production and sale of X units are related by C equal R squared over 170,000 plus 9,747. Find the rate of change of unit revenue when the unit cost is changing by $14 per unit and the unit revenue is $4,000. So that was a lot of information to soak in. So the first thing that I'm going to do, I know that I've got some variables C and I've got some variables R. All right, I'm going to write down the formula that they gave me. So this is C equal R squared over 170,000 plus 9747. Okay, something simple like that. They give it to us. All right, what's next that I know? They want me to find, and I'm going to highlight that here. It says find the rate of change of unit revenue. All right, so what are they asking me to find? They're asking me to find R prime, okay, which might be in Leibniz notation dr dt. This is the big question. Okay, so I'll write that in a different color. What else did they give us? They gave us the unit cost is changing by $14 per unit. So they told us that C prime, which is dc dt, is $14 per unit. Okay, they gave us that information as well. And they also say the unit revenue, so that right there, I'm going to highlight that in a different color. Unit revenue is $4,000. What they're saying, in other words, is that R is 4,000. Okay, R is 4,000, And I've got all of the information basically that I need in order to go about solving this problem. Okay, now all I have to do is take the derivative. And again, this is like a big implicit differentiation problem. You account for the rate of change of everything though, every variable in this case. So starting off, and let me write in a different color, the derivative of c is just c prime, so that's good to go. And then the derivative of r squared is 2r, but then I have to say r prime, and I divide that by 170,000, just like that. And the derivative of 9747 is just 0. All right, so there's not much to it there. There's the derivative. Now all I have to do is plug in the information that I know. Of course, you can reduce this fraction. The 2 over 170,000 does reduce. So you can simplify it a little bit, make your life a little bit easier on the calculator, or maybe if you're doing it by hand. So r prime over, and then it becomes 85,000, I believe. Yep, 85,000. So then you have something like this. Now, what is it that we're solving for though? We're trying to solve for r prime. So I am going to highlight that variable right there because I need to isolate it. All right, so I'm going to say this, of course, equals my c prime. So I'm going to have to multiply both sides by 85,000. Let me do that over here on this side. 85,000, so that I can get rid of this. And then lastly, I'm going to have to divide by r. Divide by r. And this right here will equal my r prime. So you manipulate the formula to get what you need. And now I'm going to ask myself, do I know c prime? Do I know c prime? Yes, I do know c prime. Oops, take that back a second. I do know c prime. Right here, it was this part in green that I got earlier, and I'm going to highlight it now in green based on what I wrote down. And do I know r? Well, yes, I actually do know r. It's this $4,000, all right, that I was given earlier as well. So now that I've got all of that information, I can find r prime by plugging in the known quantities. And that is to say that 14 gets multiplied by 85,000. And then you divide that by r, which is 4,000. You plug that in the calculator, and you're going to get something like $297.50. So this is your r prime, or your dr dt, if you will. But what is that? Okay, that right there is the rate of change of the revenue. So as the cost is changing, this is the rate of change of revenue. Okay, so it's interesting to see something like this. Sorry about that. It's interesting to see something like this because you have various applications of different things that you could do with these kind of problems. Okay, so that's one example. Let's go ahead and take a look at another example. So let me go ahead and pull that example for you. Here's the other example. All right, I like this one. It says water is falling on a surface, wetting a circular area that is expanding at a rate of 4 millimeters squared per second. And it says, how fast is the radius of the wetted area expanding when the radius is 149 millimeters? And then it says, round your answer to 4 decimal places. So let's think about this for a second. They didn't give us a formula in this case. But if you go back to the problem solving process, you know, I mentioned that. Okay, so let's take a look at that problem solving process real quick. I said, draw a picture. Name the variables and constants. Write down numerical information. Write down what it is you're asked for. Write an equation that relates to the variables. So we've got to do all of that. All right. So let's think about this. A circular, let me underline it. A circular area. Okay. I should be thinking right now, area of a circle is pi r squared. All right, now I'm also going to draw a circle, and I know that my circle will have a radius r, and I'm actually going to draw it as an arrow out because remember, this is expanding. Okay, it is expanding. They told us it was expanding. All right, so they say the rate at which is expanding, okay, the area is expanding at 4 millimeters squared per second. So what did they just give us? They said the area is expanding at a rate of 4 millimeters squared per second. Expanding is also a key word because that tells us it's getting bigger. That means it's positive. The rate is positive. Okay, so let's see what I can write down here for a second. I'm going to write down here that A prime, which is suppose dA dt, the rate of change of the area with respect to time in Leibniz notation, is 4 millimeter square per second. What else do I know? The question, how fast is the radius of the area expanding? Okay, so they just told me what I need to look for. I need to look for, suppose, and I'll use a little r, r prime. They want me to find dr, I'll write that again, dr dt. They want me to find that, okay? All right, so I find that, and I'm good, all right? And then they say when the radius is 149 millimeters. So they gave me some information about the radius. It's 149 millimeters. Okay, now all I have to do is take a derivative, right? I take the derivative, and then I solve for my r prime. So a, derivative of a, is going to be a prime. Pi is a constant, so that's going to stay there. But the r is not. We bring the power down, so we're going to say 2 pi r, and then r prime. Well, I'm solving again for r prime, all right, which I'm going to highlight once more in blue. So I want to isolate that. So in order to isolate that, I've got to divide both sides by 2 pi r, 2 pi r. Okay, so now that I have r prime equals a prime divided by 2 pi r, let's see what I know. Well, I do know a prime. All right, that was this part over here that I'm highlighting now in yellow. And I know pi is a constant. And I know r is this thing that I highlighted over here in green. And I'm going to highlight it down here in green. And that's 149. So now I'm just ready to plug in what I know. That is to say 4 millimeters squared per second divided by 2 times pi times 149 millimeters. Okay, you can kind of do some dimensional analysis there and realize that it becomes millimeters per second in terms of the units. When you do this calculation on your calculator, of course, I think you're going to get something along the lines of 0.0043. All right, 43. What is that? 43 thousandths. You get something like that, and you get millimeters per second. Okay, because one dimension of the millimeters ends up eliminating itself. Okay, so you have that right there, and we've solved the problem. Okay, now let's take a look at one last problem here, which I'll drag over to our side of the screen. There it is. Problem number 8. This one is a really nice problem. These are pretty famous, these right here, when you look at this one. Okay, and it's a nice problem. It says water is discharged from a pipeline at a velocity v in feet per second given by v equals 1264 p to the 1/2 power, which is a square root of p, if you will, where p is the pressure in psi. It says if the water is changing at a rate of 0.415 psi per second, find the acceleration dv dt of the water when p equals 60 psi. So what is this relating? It's relating velocity to pressure in a pipe. Okay, and they're talking about the rate of change of volume versus the rate of change of pressure, and it's quite an interesting thing when you think about it. Okay, perhaps you're working like in an oil pipeline or something, and those jobs are actually quite a lot of people these days are interested in working like in the oil industry and stuff like that. But think about it, you could get further along the way in a career like that if you knew something like calculus, if you knew something like this. Okay, so let's write down what it is we know. We know the formula that they gave us: V equal 1264 p to the 1/2 power. Okay, um, they tell us the water pressure is changing at a rate of 415 psi per second. So water pressure is changing. That means that right there is our P prime. All right, and it's going to be 0.415 psi. There we go, per second. All right, so I'm going to highlight that in yellow just to save myself time in a bit. All right, and then they say find the acceleration, which is in this case the velocity, not the volume. I said volume earlier, but it's actually a velocity. Find the acceleration, which is the rate of change of the velocity, which we're going to call v prime. This is what we're looking for, dv dt. We don't know what it is, but let's highlight that in blue. Okay, when the pressure is 60 psi, so they gave us P equals 60 psi, so I'm going to also write that down. P equals 60 psi. Oops, did that backwards, transpose that. All right, 60 psi, there we go. Okay, so now we take the derivative of that v function up at the top, which is the function for velocity. V prime equals 1264 times, we bring the power down, 1 over 2 p to the negative 1 over 2, something like that. Okay, and then we have to say p prime. We have to denote that we took the derivative of p. Okay, so you can clean this up, scrub this up, basically by multiplying this. Okay, so you could say v prime equals 1264 divided by 2 is 632 multiplied by p prime. And this, the fact that it's a negative exponent here, kicks it to the denominator. So you're going to divide then by p to the 1/2 power, which is basically the square root of p. All right. So I could write it like that. That's okay, because we're going to plug this in the calculator anyways. All right. So I've got everything that I need. Let's just match up everything. First thing, p prime is this part in yellow. That's where I'm going to plug that in. P is this part right here in green, and v prime is this thing that I'm looking for in blue. So not much to it after that. There's no real need to solve for v prime because it's already set up that way for me. So that's nice. So I'm going to say 632 times the rate of change, which is 0.415 psi per second, all divided by the square root of this 60 psi. All right, and that right there is going to give me, when I plug it in the calculator, about 33.9, and the units are going to be feet per second squared, because it is a rate of change of a rate of change. The rate of change of the velocity is the acceleration. So this is what we're looking for in terms of v prime. All right. So nothing to it. This is your dv dt, but some really nice application problems. And you'll run into problems like this, you know, online or somewhere else. They're good problems. Take a look at them, try to understand them. I hope this video was helpful. And as always, like and subscribe.